Okay, good morning. So today we're at section 4.2, obviously, the mean value theorem. This is a very, very important theorem, code name. It's the MVT, not the MVP, the MVT, okay, the mean value theorem. Guaranteed you will use this on your AP exam if and when you take it for a justification, okay? Really important, you need to know this one inside now. So what it says is, if y equals f of x is continuous at every point on the closed interval a to b and differentiable at every point of its interior a to b, then there is at least one point c in a b at which f prime of c equals f of b minus f of a over b minus a. Well, let's come back here a second before we get there. Really important. Criteria must be met. Got to be continuous. What does continuous mean? Continuous means that there are no breaks, jumps, or holes in the function. It's continuous at every point in the interior and the exterior. There are no breaks, jumps, or holes in this graph. Okay, and that's on every point in the interior. And also notice it's continuous on the closed interval. Okay, it has to be differentiable. Ooh, that's kind of dark. Differentiable at all its points in the interior. Well, what does that mean? That means inside this function needs to be rico suave. It needs to be smooth. Okay? It's got to be really smooth. There are no sharp points anywhere. Okay? And it only needs to be differentiable on its interior. Okay? So the derivative does not need to exist at the endpoints. Okay? It needs to be continuous everywhere, including the endpoints. And it needs to be differentiable or very smooth in the interior with the exception of the endpoints, because endpoints are kind of sharp, okay? And this point C they're talking about, this is simply going to be an x value. That's all it is. Notice, it's an x value. Simply put, I think you know what this side is. I hope you know what this side is. Hopefully you know this is the A rock. That is the A rock from A to B. It's the average rate of change. F prime of C, and notice C is somewhere between A and B. This is the I rock at C. Okay? So when does the I rock equal the A rock on a particular interval? Well, hopefully I got you good and confused already. And let me draw you a little picture of this. So let's say I have some point here, we're going to call it A, and then I have a continuous function and it's going to go to B. And it can do whatever it wants, and I can come right up here and I can say there. So somewhere within this interval, I don't know that it doesn't matter. Somewhere in this interval, what's going to happen is this side, because it's the A rock, okay, it's the slope of the line connecting A and B. Okay, so that is, oh, I got to come here first. I need a line. It's going to be the slope of that line. I'm going to make him red. So it's going to be the slope of that guy that is connecting these endpoints. Okay? That is my A rock. That's my average rate of change. That is slope of that line. Okay? Well, what this mean value theorem says is somewhere inside A and B. Somewhere inside A and B, as long as it's continuous and differentiable, there exists some point, and we're going to call it C. I'm going to throw that little bugger right about here, and that little C is going to be right here, such that the instantaneous rate of change, or the IROC, or the line tangent to the curve at point C, is going to be equal or parallel to the average rate of change. That is what the mean value theorem says. It guarantees me, as long as it's continuous on the closed interval, differentiable on the open interval, it guarantees me that there is at least one C value in A and B that equals the average rate of change. Okay? Sometimes there could be more. In the one that I just drew here, yeah, there could be another C here that is going to be tangent to that. But it doesn't guarantee me there's more than one. It just guarantees that there is one. Okay? And bottom line, it's the slope of F at C, meaning it's the IROC at X equals C. That equals the AROC from A to B. Okay? I like to kind of think of this as grandma's theorem or whatever, holiday theorem. Okay? Let's think about this. If grandma lived 150 miles away, Grammy Graham was 150 miles away, and you got there in 2 hours, what's your average rate of change? Well, it would be 150 divided by 2, which would be what, 75 miles per hour? Okay, hopefully you're on the interstate, not the 2-lane highway. All this theorem guarantees that at some point, at least one point during these 2 hours, you were going precisely 75 miles per hour. That's what grandma's theorem tells us. Okay? At some point, if my average rate of speed went there, then at some point I was going 75 because I might have been doing here's my 75, and I might have been, just walking along somewhere in there. I'm going to get there. It's when the AROC equals the IROC. Let's roll, okay? Example, state whether or not the function satisfies the hypothesis of the mean value theorem on the given interval. If it does, find the value of C that lives within the interval A to B. Find the X value inside A and B that satisfies when the IROC at C equals the average rate of change over the interval. Okay? Well, what do we have to know? There are two criteria I need to have. Am I continuous on, and it has to be a closed interval, is this function continuous? Well, heck yeah, it's a polynomial. They are continuous everywhere within their domain, which happens to be all real numbers. Is it differentiable on the open interval from 0, not A, 0 to 4? Well, heck yeah, polynomials are rico suave, as I said. They are smooth, smooth, smooth. Therefore, they are continuous and differentiable everywhere in their domain. So, yes, the mean value theorem does apply. Yes, MVT does apply. Okay, so what we're going to do is, bottom line, we want to find out our AROC. What's below there? I need a little bit more room. Okay, there we go. We need to find out my AROC. What is my AROC from 0 to 4? Well, that is going to be basically y of 4 minus y of 0 over 4 minus 0, right? Okay, well, what does that have to equal? That has to equal my derivative. But what's y of 4? Well, if I plug a 4 in here, I got 16 minus 12 plus 1. So what do I have? 4, is that 5? Minus 1 over 4. So that is going to equal 1. Okay, I need to know when is y prime, which is 2x minus 3, when does the I rock equal the A rock? Okay, so I'm going to bring that down. When does 2x minus 3 equal 1? Well, 2x equals 4. It would be when x equals 2. Now notice, I have to triple check. Is this value I found in that interval? Why, yes, 2 is between there. Therefore, c equals 2. Okay? Because if I came back here and I said, what is y prime of 2? Y prime of 2 is going to be 4 minus 3. It equals 1. The instantaneous rate of change equals the average rate of change at point C, which is really an x value at x equals 2. That is the mean value theorem. And it's really kind of a nice theorem. It's not very mean, just so you know. Okay? So we're going to look at the next one. Well, when we're talking about this continuous and differentiability business, like I said in the beginning of the year, your parent functions really, really help. Okay? Because hopefully you can look at this little rascal here, and if I graphed an absolute value function, this little devil, the vertex is shifted over right here. It's got a slope of 1 going up one side, a slope of 1 going up the left side, and I'm at negative. So I want to know between here and 1 to here, is it continuous? Well, yeah, it's continuous on that interval from there to there. But is it differentiable? It is not differentiable. That is a corner. Therefore, not differentiable. Therefore, mean value theorem does not apply. Okay? Therefore, it doesn't apply. What am I going to do? Well, I'm only going to state the value C if it does apply. It doesn't apply here, so I'm on to my next problem. Ooh, we got a piecewise function, little critter. Well, what do we need to know? Is the A rock equal to the I rock? Let's see. Can we find the value C? Well, I need to make sure first is y, not y prime, sorry, is y continuous? Well, I know the upper piece is continuous because it's a parabola. I know the lower piece is continuous because it's a line. They are both polynomials. But is it continuous where they come together? The question is y continuous at x equals 1? Well, the way to find that out is I need to know what's the limit as x approaches 1 from the right of y. Is that equal to the limit as x approaches 1 from the left of y? Okay? I can see y, if 1 is defined, what is the limit as I approach 1 from the right? Well, that would be, this would be my right side. So if I plug 1 in there, I get 3 times 1 is 3 plus 1, I get 4. Is that equal to my limit as I approach from the left? I put a 1 in here. 1 squared is 1. 1 minus 1 is 0. Ooh, it's not continuous. Therefore, mean value theorem does not apply. Therefore, I can't find C. All right, brings us on to the next one. Almost the last one here. We got a trucker. Ooh, a trucker is handed a ticket at a toll booth showing that in 3 hours, check it out, in 3 hours, she had covered 229 miles, okay? She had covered 229 miles on a toll road with a speed limit of 65 miles an hour. Was she cited for speeding? Yes. Why? Because she is a woman. Just kidding. Because she's a bad driver. No, I don't know. Okay, so what do I need to figure out? Well, how many miles did she cover? What's her average rate of change? This is grandma's theorem at its best right here. Did you know they can actually do this? They got tollways all over. She covered 229 miles in 3 hours. That means she was going at least 76.333, 76 and a third miles per hour at one time. Well, can they prove that she was speeding? Yes, she can. How? Well, her average speed over the 3 hours was 76. That means she had to be going. Now think about this. You're a truck. You're driving a truck. You started at point A. You ended at point B. Closed interval because I got a starting point and a stopping point. Did this truck just like magically blink, snap? Did she snap her fingers and all of a sudden she was 50 miles ahead? No, she started and went, and then got to the toll booth. It was continuous, okay? Is she differentiable? Meaning, can she instantaneously change her speed, change her rate of change, or does her rate of change need to increase smoothly as she accelerates the truck? Well, of course it's got to be smooth. She's differentiable. Therefore, this problem, we know the function modeled by it would be continuous and differentiable. Average rate of change was 76.33. Therefore, yes, she got a ticket. Got a ticket. Why? Because the mean value theorem showed 76.333 miles per hour average. Guaranteed she was going at least 76 and a third miles per hour at least once. Okay? Here, this one's for you. Why don't you try this? Hit pause, give it a shot, and I'm going to come back with it. Actually, no, I'm not. You hit pause, I'm just going to work it out. Okay? So, polynomial, continuous, differentiable everywhere. Therefore, mean value theorem will apply. I need to know when is f prime of c equal to the A rock from A to B. So I like to think of this, what is my A rock from A to B? Well, that's going to be f of 5 minus f of 0 over 5 minus 0. That's going to be what? Well, what is f of 5? Well, that's 3 times 25, so that's 75 minus 30 plus 7, right? So what is that going to give me? That's going to give me f of 5 is going to be 52 minus f of 0. Well, that's just going to be my 7. That's going to be divided by 5, which turns into 52 minus 7. What is that? That's 45 over 5. Her average rate of change would have been 9. Well, what do? We need to know when is f prime of x, which would be 6x minus 6, wouldn't it? When is this equal to 6? What x value equals 9? 6x is going to equal what? 15. Therefore, x has to equal 15 sixths. 15 sixths is approximately, it's just under 3, isn't it? It's 2 and 3 sixths, or 2.5, would it be? What's that going to be? 5 halves, so it's going to be 2.5. And 2.5 falls between 0 and 5. Therefore, C equals 5 halves, or 2.5 for the decimal freaks. Okay? And what we're going to do is I'm going to fire up my next notebook. You guys are going to roll on to 4.2b, and I'm going to be back here in a minute. We're going to do a little bit of that one yet too. Okay, I'm back for the attack here. We are going to be predicting hidden behavior again, except we're going to talk about our very rigorous first derivative test that I have been talking about the past couple days. And derivative, remember what the first derivative talks about. That talks about when my function is increasing or decreasing. So if a function increases and it decreases, I got a maximum. If it decreases and it increases, I got a minimum. Well, isn't that a little fancy? And don't forget, hidden behaviors, okay? Hidden behaviors. Well, that's what we're doing for predicting these. We're using the derivative to discuss what a graph looks like. What do you mean what it looks like? Where is there a max or a min? Where is it increasing or decreasing? Where is it concave up or concave down? Where does it have a point of inflection? All these things we want to discuss without the graph, okay? So we're going to look at our first derivative test, and this is the test for increasing and decreasing functions. Well, bottom line, if f prime of x is greater than 0, that's just saying it's a positive value at each point in A to B, in each point within a particular interval, then we know f is increasing on A and B, meaning left to right it's going up. If the derivative is less than 0, that's just simply put, that means it's a negative value within a particular interval. Well, then f decreases, meaning from left to right, reading the graph, it's going downward, okay? And this is our first derivative test. Doesn't it sound pretty tough? So for the following examples, find the domain, extreme values, and intervals of increasing and decreasing for f of x. Well, these mean I need critical points, intervals of increasing and decreasing. We're going to be able to do this based off of our critical points, okay, and our very rigorous first derivative test, okay? So first and foremost, what is the domain of this guy? This is a cubic function. This is a polynomial. The domain of those are all real numbers. They are continuous. They are differentiable everywhere, okay? So now to find my extreme values, I need my critical points. Critical points happen when f prime of x equals 0 and when f prime of x does not exist. Okay? Well, because this is a polynomial function, rico suave, it always, the derivative exists everywhere because they're continuous and differentiable everywhere. Well, let's figure out where y prime is 0. So that's going to be 2x squared minus 4. Really, oh, yeah, 2x squared, I was going to say, oh, boy, why did I put a 2 there? Come on, you knothead. Oh, boy. It's because you guys aren't here to keep me on my toes. So, y prime actually equals 0 here when x plus 2, x plus minus, I'm on fire because I'm rushing, minus 2. So I know when x equals negative 2 and when x equals 2, I have critical points, okay? Critical values. Okay, I got one at x equals negative 2 and I got one at x equals 2. From here, we're going to use this ridiculously crazy, okay, rigorous first derivative test. And what this first derivative test is going to be testing, we're going to test it on a number line. So this is going to be my y prime line. And what I'm going to do, I like to see 0 on my line. And I know here at negative 2, my derivative is 0. I know out here at 2, my derivative is also 0. Prove that right over here. Okay? I want to know, negative infinity is down here. Positive infinity obviously is here. I want to know what it's doing between these critical values, because if I had a change from increasing to decreasing or decreasing to increasing, why wouldn't I have an extreme value? Okay? So all I'm going to do is I'm going to pick any point within an interval. And I like to work my way from left to right. So I'm going to pick, say, -3 in that interval. And what is y prime of 3? Now, y prime of 3, yeah, it's going to be -3 squared minus 4. Now, is it going to be a positive or negative number? This is the key. The key is not that it's 5. The key is that it's positive, because now I know my function is increasing here. Okay? Then I'm going to pick 0 in the middle of my critical points, and when I plug that in there, I know y prime of 0, hey, that's going to be a negative number. I can see it. It's right there. It's -4. So I'm decreasing in here because my derivative is negative. And then I'm going to test 3 out here, and I can see, well, what's it going to be? Another 9 minus 4. And what I like to do is I like to put my 3 in here and say, that's going to be a positive. That's going to be a positive. A positive times a positive gives me a positive value, so I'm increasing again. Therefore, what I'm really looking here is I'm looking at that flat, increasing it, max, and then I decrease, then I increase, min, okay? So that's what I'm looking at. So I know my domain up there, I already stated. I know that I'm going to have f of -2 is going to be a max. Do I have to find it? I don't know. F of -2, well, I will quick. F of -2, well, then I got to come here, put -2. No, we're not going to find it. We're just going to say it's a maximum. I'm going to say max at x equals -2. Oh, nope, they want extreme values. Back up the train here, Kruger. Okay, so I need to find my values. So I got to come down here and say y equals 1/3 x cubed minus 4x. So I need to find them. Okay, I know f of -2 is going to equal, well, when I plug it in there, I got it written down at 16/3. Therefore, that was a max. And f of 2, very symmetrical, -16/3, minimum. And I know I'm increasing and decreasing where? Intervals. Well, I start increasing at -∞ all the way up to my critical value of -2. Then I decrease from -2 to 2. Then from 2 to infinity, I increase. Okay? And a lot of times you're going to have to justify why you know it's increasing. Well, why do I know it's increasing? Because y prime is greater than 0. Why do I know it's decreasing? Y prime is less than 0. That's how I know. Okay? And then we're going to do one more quick example here, and then I am out. Right? And I'm going to hit pause here. No, I'm not. I'm going to do it up quick. Domain. All real numbers, x, except 0. Can I have an extreme value at 0? No, because it's a vertical asymptote in my graph. Okay? Extreme values. I want to see this guy as x to the -2. Therefore, my derivative equals -2 x to the -3. So my derivative in a nice looking form is -2 over x cubed. Well, when does f prime of x equal 0? Never. Why not? Because there's no way to get the numerator of that fraction equal to 0. When does f prime of x equal, when does it not exist? It does not exist at x equals 0. Okay? So I have a critical value. So I'm going to take my derivative line, and I know here at 0, my derivative does not exist. Here's infinity, -∞. That's a crappy infinity. This is my y prime line. No, it's not. It's my f prime of x line. And what I'm going to do is I'm going to take, say, -1. I'm going to test it. what's f prime of negative 1? Well, it's going to be negative 2 over a negative 1. It's increasing there. How about 1? What's f prime of 1 going to be? Well, it's going to be negative 2 over 1. It's going to be decreasing there. Okay? So I know I'm increasing from negative infinity all the way up to 0 because y prime is greater than 0. I know I'm decreasing from 0 to infinity. Why? Because y prime is less than 0, or f prime of x, I guess I should probably be saying. Do I have a maximum value? Well, what the heck is f of 0? What is 1 over 0 squared? It's undefined. I have no extreme values because at this point on the original function, that point does not exist, therefore it's undefined. Okay? That is the end of today. Have a good day. See you Monday.